Hi everyone, I am Sanya Kuller and this is cute little Yangshi. And this is the short version of the video on conditional independence. So please do check out my longer video if you have more questions, and please do reach out with any questions at all, and please do subscribe. In this video, we're going to be talking if you're given a joint probability distribution table. How do you find if two random variables are independent conditioned on another variable? So please note that the question then is, given random variable C, are random variables A and B, are they independent? So are A and B independent of each other given C? So the formula that we'll be using is to see if the probability of A and B, given that C has occurred, is that equal to the probability of A given C multiplied by the probability of B given C for all values of A, B, and C. So this is sort of what this represents. So we're not sure if these edges should be there. But if indeed random variable C, given that it occurs, if it makes A and B be independent of each other, like in this situation here, if there's no more uncertainty, if the probability of A and B given C equals the probability of A given C multiplied by the probability of B given C, so if A and B are independent given random variable C, that's what this represents here, then this is sort of like a Bayesian network. And in this case, this would be like a common cause, where each of these directed edges is a conditional dependence. So please don't worry about it too much in this short video, but I do have other videos talking about this. But we were going to talk in this short video how to see whether or not A and B are independent of each other given C. And independence is given by this upside down T sign. So A and B are independent given C in this diagram. But we're going to test and see how we can test if this is the case. So again, please do watch my longer videos and please do subscribe for more updates. And this is an example of a Bayesian network, a mini example with a common cause where A and B both come from their parent C here. So please note that this video is going to be a very quick kind of overview about how to determine conditional independence. That is, are A and B, are they independent of each other given some other random variable like C? So this is going to be much faster. I'm just going to show how you would derive it, and I'm just going to be very quick in this video. But I do have a longer step-by-step video on YouTube, a longer version on how we can do this conditional independence and what is the intuition, and I work out many more numerical examples. So please do check that out. Yangshi, he's very similar to my shirt here. He's also saying, please check it out. Basically, what the question is saying is A independent of B given C. So the given C part is just referred to this part, given C, or given C part here is just given C, given C, given C, and this is the same given C. So is A independent of B given C? So typically, you can just think of this as just saying given C, we're just tacking this on here. Because we can define two random variables as being independent in an unconditional model, and I have another video on this, so please do see this out, like are A and B independent as we'd seen, right? So this means and here. So what this means is, and that's what that caret means here. So A and B are independent if the probability of A and B equals the probability of A multiplied by the probability of B. And this is the unconditional model. This is when we just think of A and B being independent. However, In this video, we're talking about a conditional model. And what makes it conditional is the fact that we're given C here. So probability of A and B given C. If that is equal to the probability of A given C multiplied by the probability of B given C, then we can say that, A and B are independent of each other given C. That's what we get from the conditional model. And we can say as is. So A is independent of B given C. So this term right here, like that well, but here this means independent. You could just say that A is independent of B. And from this one right here, we can see from the conditional model that A is independent of B given C. So based on what we've seen, so probability of A and B given C equals probability of A given C multiplied by probability of B given C if A is independent of B given C. So again, adding in the given C means that we add in this given C here, this given C here, and this given C here. So each part we add that on. And as we just saw from Bayes' rule right now, these are the same here, and these are the same here. So basically what we can just see, in other words, is that, if A is independent of B given C, then, probability of A and B given C is just equal to this probability. So in other words, it's the probability of A and C multiplied by the probability of B and C divided by the probability of C. That's all that it is. It's all just a matter of speak. If we want to see if A and B are independent, given C, just have to tack on this given C part here, given C here, given C. And then all the corresponding probabilities were the same, except that we're just tacking on this given C here, given C. Like that's all that's happening. So it's an independent test for seeing if A and B are independent, given C. Thus, we really need all four of these statements to be true for A to be independent of B given C. Since C is a Boolean random variable, it's essentially an event, it can have these two possible outcomes. C can be true or it can be false. So as you see here, I've just said given C. So the way that you can think about it is we have our C here now, and we can see our C, and C is for cat. Hi, Yankee. C, this little cat, can be true or it can be false. So true or false. And then, so like if C is true, we have our A, B over here. And again, we have the four sets of values that they can have. False, false, both false, false, A false, B true, A true, B false, or both true. And then we can see the same thing here for both of them. But like see, if A is true, then we have conditional probabilities that we observe for A and B. We have the probability that A is false and B is false, given that C is true here. A is false and B is true given C is true. A is true and B is false given that C is true. And A and B are both true given that C is true here. So these are all given that C is true. So they're all conditioning on this over here. And we're determining them, and they could change these probabilities that we observe these events. They can change given that C is true. But if C is false, what we're going to notice is that instead these probabilities are defined, these same events of A and B being true or false or what the values are going to be given that C is false. So out of the situation when C is false, what are the probabilities that we observe, the events that we observe? So they're going to then differ. But since this is a conditional probability, we have to condition. We know given that a certain outcome, either C is true or false. So we have to be specific now. And now you can see, whereas before what we were essentially doing was just like ignoring, all of this stuff here. We weren't even considering, and even for the next table too, we just were not considering any of this part here. Not at all. We were not considering it, so we had just four unique outcomes, these four outcomes here. We did not consider, if we're just testing if A and B are independent, we did not consider B at all before. But now, since we're now looking given that C is true or false, we have these 8 possible outcomes. So for each situation for A and B, A is false and B is false. So A is, here, there, we need to consider, what if C is true? What if C is false? So for each set of all outcomes for C, we have these two possible outcomes here. So it's the idea that since we have 3 random variables now in the fray, A, B, and C, we have outcomes to consider, whereas before we were just looking at A and B, we just had these 4 outcomes, but now we're conditioning on C. So if C is true or C is false, that's going to impact the probability that we observe that both are false, for instance, so that A is false and B is true, and so on. So we have these A outcomes. And to see if A and B are independent given C, this is the formula that we use. The probability of A and B given C, is that equal to the probability of A given C multiplied by the probability of B given C for all possible values of A and B. So we can have, so let's say that C is true, then we can have A is false, B is false, A is false, B is true, A is true, B is false, A is true, and B is true. So both of them being true. And then if we look at this formula, then we need to see and calculate this. This is the conditional probability given C is true. So we would need to find probability A is false and B is false given C is true, and see if that equals probability A is false given C is true multiplied by probability that B is false given C is true, for instance. So these are the conditional probabilities that we need to calculate for each of these respective values of A and B. And there are 4 possibilities again. So 2 values for A and 2 values for B, true and false. So this is what the conditional probabilities would be given that C is true. So we see that we're conditioning here on C being true. And similarly, if instead C is false, then we're conditioning on C being false here. And we again have these 4 sets of values for A and B. False and false, false and true, true and false, and true and true. And then for the conditional probability, it's just taking the values of A and B and putting those here, and then conditioning on C being false. So we have these 4 respective values conditioned on C being false. And then we would need to test these equations to see if they hold for all these values of A and B, now if C is false. And before we were conditioning this on C being true. So now, going back to the original equation here, little Yangshi in the back. So we just need these statements to be true. So there were these 4 statements from before, and now we just need to understand that C can be true or false for each of these. And so we need to break them apart into the set of values of C. So basically for these 4, since we have 2 possible values of C, we're going to have the 8 total equations. So 8 total tests. So as I mentioned, it gets kind of tedious to do this. So basically, we need all 8 of these statements to be true for A to be independent of B given C, which is the same thing as B being independent of A given C. So, this formula, these are the 4 statements we were talking about before. So probability A is false and B is false given C equals probability A is false given C multiplied by probability B is false given C. So there are these 2 outcomes of C, C being true or C being false, and we need to condition on each of those. So again, you see 2 for each, when C is true and when C is false. So for each of these 4, we're considering C is true and C is false. C is true, C is false. C is true, C is false. So 2 outcomes for each of these 4 statements. So thus we have those 8 outcomes there that we're seeing. So A is what we're seeing here again is A is false and B is false here, given that C is false equals probability A is false, given that C is false, multiplied by the probability B is false, given that C is false here. But in this next example, probability A is false and B is true, given C, is equal to the probability A is false, given C, multiplied by the probability B is true, given C. And we need to then consider those outcomes of C. So, what if C is true? Then we need to see if the probability A is false and B is true, given that C is true, equals the probability that A is false, given C is true, multiplied by the probability B is true, given C is true.
but then C could be false. And then all we have to do is we just have to change this value of C to being false then, which is what we do on the second part here. But we're seeing the probability A is false and B is true, given that C is instead false. Is that equal to the probability A is false given C is false multiplied by the probability B is true given that C is false? Then we're also testing this third statement, which is, A is true, probability of A is true and B is false given C. Is that equal to the probability that A is true given C multiplied by the probability B is false given C? And C could be true or false. So we need to consider those outcomes of C. C being true, 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 or C being false, false, and false. And lastly, we need to see if probability that, A and B are both true given C, if that's equal to the probability that A is true given C, multiplied by the probability B is true given C. So all we do is we add in, what if C is true? Then true here, and true here. We put in true here, here, and here. But if C is instead false, then we just put false here. False, false, and false. So there are these 8 outcomes that we have, which I've highlighted for you guys. Yay, highlighter. Thus, we really need to test that all 8 of these statements are true. So conditioning on C being true or false, we need to test 8 statements. That's why I was saying that sometimes if we're doing these Bayes rules, it may even be better that you find like at some point one of these is not true, and then you can just say A and B are A is not independent of B given C, which is the same thing as B is not independent of A given C. So if even one of these 8 fails, then you can say that A is not independent of B given C. So otherwise you need to test all 8 of these. And if all 8 of these are true, then A is independent of B given C. Otherwise, A is not independent of B given C. If even one fails, if so if at least one fails of these fails, if at least one of these fails, then B and A. So A is not independent of B given C, which is the same thing as B not being independent of A given C. Otherwise, we have to test all 8 of these, Yangshi. That's a lot to test. And if all of these are equal, then A is independent of B given C. Thus, we need all 8 of these statements to be true for A to be independent of B given C, or equivalently, B is independent of A given C. So these are the 8 same statements, and because we are not sure yet, I'm going to put a question mark over the equal sign because we're not sure, but we need to test that all 8 of these hold true. And if all 8 of them hold true, then A is independent of B given C, which is the same thing as saying that B is independent of A given C. As I was mentioning, it's just a matter of speak. But if one or more of these is false as you're checking along, then A is not independent of B given C. Then that's not the case, which is the same thing as saying that B is not independent of A given C. So sometimes this is better, as I was mentioning, because if this one or more of these being false, otherwise you're stuck going through all the calculations. But yes, it's pretty rigorous to show that A is independent of B given C, but it's just kind of like applying the math repeatedly. So then what we need to do is we need to obtain the probabilities from the joint probability table. So what we're going to first focus on is the probability of C values that we need, because as you can see, pun intended, that we do use C a lot. So we need to find the probability that C is true. So you can see from this joint probability table that I've sort of pieced it together, where I have the C values here and then the true and the false values here. And then to find the probability C is true, I just have to add all these respective values when C is true here, these four outcomes. So that's 0 plus 0.3 plus 0.2 plus 0.2, and that is 0.7. So the probability that C is true is 0.7. Then the probability that, so basically to verify, this is just 0.7 here. That is the probability that C is true. And the probability that C is false is just taken by outcomes when C is false. So we add the 0.3 plus 0 plus 0 plus 0. So that's 0.3 here. That's the probability that C is false. And we just have to add these numbers together and make sure that they add up to 1. So again, all these outcomes, 0.7 plus 0.3, they add up to 1. So that's great. So we have these probabilities to work with. So probability C is true is 70% and probability C is false is 30%. If you want to find the probabilities where C is true, we sort of just have to focus on this joint probability table and just eliminate the situations when C is false, which are these last four rows. As you see here, C, pun intended, C is false here. So we're just focusing on the top, which is where C is true. And then we want to gather the probabilities that we need, which is the probability that A is true and C is true. Probability A is false and C is true. Probability B is true and C is true, and probability that B is false and C is true. That's what we want. And what you'll see here, when intended, is that if we're looking at the probability that A is true and C is true, so that part is just going to be A is true and C is true. So since all of these are true, essentially, we're just focusing on the values of A over here. So A is true and C is true. That's this part here. So this one will be given by 0.2 plus 0.2 here, which is 0.4. So these are, it doesn't matter if B is false or true. And I kind of explained this more in another video, how we do this. But it doesn't really matter what B is. We just care about A being true and C being true. And then here, if we are looking at A being false and C being true, instead we're focusing on these here. We're focusing on these rows here. That's what we're focusing on here, the top part. And then we're going to have 0 plus 0.3, which is just 0.3 here. So again, it doesn't matter if B is false or true here. Now one of the steps, so you see that, pun intended, so you're seeing here, essentially that we have these four outcomes here that we have used. For A is true and C is true, we highlighted these two yellow ones here. That's what we highlighted here. And then for A is false and C is true, we have these orange here. Is it a little orange cat toggle? So these should collectively sum up to the probability that C is true, because again, we didn't really care if B is false or true. We just care about A and C here. So if we add all of these up, which they should add up to the probability that C is true, which is just 0.7. You can see this visually as well because we used all four rows where C is true. And we found earlier the probability C is true is 0.7. But just to kind of show you as well, so if we add this plus this, essentially because A can be true or false, that means that for any value of A, essentially adding up on A crosses out, it crosses out like A essentially, because you're crossing it out because A is true or false and you're considering both. So what you have in the end is C is true, which is 0.4 plus 0.3, which is 0.7. So again, this is 0.4 plus 0.3, which is 0.7, which is indeed the probability C is true. And similarly, if we can focus on B instead. So what we can see here, yeah, I won't be annoying about the C part, but anyways, is that we can focus on probability B is true and C is true here. So C is always true because of what we have subsetted it here. So if B is true, this part here, this is just 0.3 plus 0.2. It doesn't matter here what A is. So the probability B is true and C is true is just this 0.3 here plus this 0.2 here, which is 0.5, 50% of the time. Again, we're controlling for any value of A, the false value, which is the 0.3 part, and when A is true, which gives us the 0.2 part. And then, lastly, we want to see when B is false and C is true, and again, A can be true or false. So then we have, for this part, we have the 0 plus 0.2, which is just 0.2 here. Because B is false and C is true, B is false, C is true, that's what this gives us. And again, if we verify that we add this 0.5 here, if we add this 0.5 and this 0.2 together, they equal 0.7, which is probability C is true. So right now you see it like this, but just for you to also just check that you've added them up correctly, because here, you just want to make sure, and you see that they add up to 70%, which is the probability that C is true. So that's great. So this added to 70%, this added to 70%, and these are just different slices, probabilities based on the variable that you're using, A or B, given that C is true. And then we can do the same analysis when C is false. So we can see that if A is true and C is false, what that is, all of these things when C is false. So we're just going to get rid of the part of the table now, the other part, the top part, because now that's for C is true. We're focusing here instead on when C is false on this bottom half. So what we see here is the probability that A is true and C is false, and the probability A is false and C is false. So given C is false, we look at the both possible outcomes for A, the true and the false. So if we're looking at probability A is true and C is false, A is true and C is false, then we're going to have these values here. So ultimately what we will see here is that we're going to, pun intended, we will have the 0 plus the 0 here, which is just 0. That's what we get here. And similarly, if we're focused on A false and C false, then we just focus on the top part, which is A false, C false, A false, C false. And we get 0.3 plus 0, which is 0.3. And when we add those up together, these two probabilities up, essentially this is 0.3, which is the probability that C is false. So remember, this was 0.7 probability C is true, and then this was 30%, which is probability C is false. So this adds up to 30%, which is the probability that C is false, which is great. And it's again, like when you're doing this, because we're adding A is true plus C plus A is false, then essentially like we're just controlling for A both values. And it's just the same thing as probability C is false, because A can be true or false. So adding them up together essentially like negates us focusing on A. So similarly, we're also going to focus on B part of it, and we're going to see the probability that B is true and C is false. So B is true and B is true and C is false, and B is true and C is false. That's just going to be equal to 0 plus 0, which is 0. So that's what this becomes here, this probability, which is 0. And then the probability that B is false and C is false are going to be given here. and that is 0.3 plus 0, which is 0.3. So this should be a 0.3. So when we see this, then what we are observing is that, so this is 30% here, and this is 0, and this is this value here. This adds up to 30%, which is the probability that C is false. So these all work out for us. So again, this is 30%, and this is 0, this is 30%, and this is 0. So these are what the probabilities become. This is just 0.3 here. They also want to learn about probabilities, right guys? Okay, so yes. So anyways, we want to find the probabilities for A and B as well. The 4 values, it's easier because we were sorting it on C being true or C being false. You can do it either way. So I just wanted to group them together based on A and B values falling together in these categories as well. There are many ways you could write this truth table here, but because I organized it, this is how it looks here. So now if we're looking for the probability A is true and B is true, so both are true, then we're going to just see that I've grouped them together, and the only key difference between these two rows is just the outcome of C. So C can be true or false. True is and false is, so it doesn't matter. So what we see here is that we're just going to take this 0.2 that we have here and this 0, and then just add them up to get 0.2. So that's how we get this value here, 0.2, 20%. And what we see, and so since these are all 4 possible outcomes for A and B, they should add up to 1 in the end. Like that is what they should add up to. They should add up to 1. So that's what we see here. And then now we want to see probability A is true and B is false. So A is true and B is false. So that will give this to us here. A is true and B is false. That'll be like 0.2 plus 0. So that's what we have here, which is 0.2. And then what we want to do is we want to see probability A is false and B is false. So both of them are false. So what we were going to do here is we're going to say, okay, both are false. So that's just the top one, false and false. And you see that C can be true or false here. And that's what we get here, which is 0 plus 0.3, which is just 0.3. And last but not least, we see that the remaining unshaded parts here are for A is false and B is true, and C can be true or false. So that will be 0.3 plus 0, which is 0.3. And now if we add all of these up together, we have 0.2 plus 0.2, which is 0.4 plus 0.3, 0.7 plus 0.3 is 1. So this adds up to 1, which is great. Yay, we won! So these are all of the probabilities that we have gathered through our analysis and collecting the probabilities. These are all the probabilities that we have gathered, and we will be using this to be able to understand the conditional independence and see if A and B are conditionally independent given C. Or in other words, is A conditionally independent of B given C? So this is what we have as the probabilities that we've calculated, and this is our arsenal of values. So thus, please note that our input that we're going to be using is we have this set of probabilities that we have determined. And Yangxi's saying, yes, let's use it. Aww. He's agreeing, let's use this. We have the set of probabilities over here, and we have these 8 statements to check to see if these hold, and all 8 of these need to be true in order for A to be independent of B given C. So if all 8 are true, then that's the case. Otherwise, A is not independent of B given C. So we're going to use this data, and we're going to use these formulas here, and we're going to test this out. So for this first test, we're going to see if the probability that A is true given that C is true multiply by the probability B is true given that C is true, if that is equal or not to the probability A is true and B is true, that both of these are true given that C is true. So, given Bayes' rule, this probability right here can just be expressed in this formula here. As we mentioned earlier, that's how it can be expressed. And then this other probability can be expressed in this way here. Okay. So that is the probability that A is true, given that C is true from Bayes' rule. Bayes' rule. Again, I have other videos talking about this too, some more. So from Bayes' rule, as we had derived, then this formula is probability A is true given that C is true is just equal to the probability A is true, and you slash down this part here. You always slash this down on the top, and C is true. So you slash it down and make this an and on the numerator, and then this part becomes the denominator. So it's the probability A is true and C is true divided by the probability that C is true. And we had calculated that probability A is true and C is true is 0.4, and we know that probability C is true is 70%. So this probability is 0.4 over 0.7. And similarly, so that's what this one becomes. So similarly, for this probability, we find the probability B is true given that C is true equals probability that B is true and C is true divided by the probability C is true, which is 0.5 over 0.7. So we have these probabilities here, and we're just going to multiply them. So that's what we're going to do. We're going to multiply, we're going to multiply these here, this part here, and also this part here. Okay, so I'll just maybe leave it with maybe an underline of purple. Okay, so then what we do is we just start multiplying them here. So this 0.4 over 0.7 becomes here, and then this 0.5 over 0.7 becomes over here, and we're just figuring out what the left hand side is, and that is 0.2 over 0.49, which is approximately 0.408163. So this part right here, this is the left hand side. This part here, all of this calculation right here was for the left side. It was for the left side, this left side here. And now we want to find this probability here on the right side, which is A is true and B is true given that C is true. So using Bayes' rule again, all we have to do is for the denominator typically is what, we're given that C is true. That's what the denominator is. And the numerator just takes this part that we're interested in, A and is true and B is true here, and it also slashes down this given and makes it an and. So it's just saying A is true and B is true and C is true. That's what the numerator is. So we found from before, from the joint probability table, that this is 0.2, and the probability that C is true is just going to be 0.7. So when we do this, we find that this is 0.285714. So this is the right hand side. So what this value is this part is 0.285714, and this part right here is just going to be 0.408 So we definitely know that these are not equal to each other. So since probability A is true given C is true multiplied by probability B is true given that C is true, since it's not equal to this probability, A is true and B is true given that C is true, this shows that there is no independence here, that A and B are not independent given C. That is, A is not independent of B given C, and which is the same thing as B is not independent of A given C either.
So what we end up finding is that the first test actually does not work. It's false. The conditional independence test failed. So as soon as we reached that and it failed, we just stop testing the other statements. We don't need to test the other 7 because, this was a false test. This test did not work out for us. And which is actually great because if your first test out of 8 tests fails, you don't have to spend time doing the others. You save a ton of time. Otherwise, you have to keep going to the end, check the second test, third, fourth, fifth, sixth, seventh, eighth, see if each of those passes. And if along the way any of them fails, you're done and you can say that A and B are not independent given C. But if all 8 pass, then you can say that A and B are independent given C. We needed all 8 of these statements to be true for A to be independent of B given C, the same thing as B being independent of A given C. And so we still haven't done these other 7, but we found from the first one that this is no, no, no. This did not work out. So what this means is that, one of these failed and we needed all 8 to be true. So again, that's exactly why we said that, A is not independent of B given C. The same thing as saying that B is not independent of A given C. We didn't even need to check these other ones. And that's a great part. We saved us, some time to check these other 7. But in case you're going to wonder, I'll give you the answers, but, we don't even need to test these. So we just had to test this first statement here. And then we just don't even need to test them because this part is what we're seeing. This part means it's not equal to. We needed all of these to be equal. So, we don't have to do this. In this video, it's shorter also because I'm not walking through these other ones. And I have a longer video just going through all of these as well, where I show for each of them. But in case you kind of want to solve it out and double check, what are the actual solutions? Then what you would have found if you walked through and tried these out is that these first four, they end up being not equal. This one's not equal, not equal, not equal, not equal, and the last 4 end up being equal. So because the first one again was not equal, we just said that they're not conditionally independent given C. So, but this is what you would get if you were to solve out the others. And again, I have a long video on YouTube going through all of that too, in case you're wondering.
If I ask the question, given this joint probability table, is A independent of B given C? The answer is no. A is not independent of B given C. There is at least one situation where that is not the case for one set of values of A, B, and C, but in fact we found 4 such situations, and those usually center around C being false in our situation, as you can see.
So again, I'm Sanya Khutter, and this is Cute Little Yangshi.